Okay, so maybe I want to ask if you have any question on previous material, but I'm also going to review some of those. If you don't have question at this moment, you can wait until when I review the material. But if there's any question, maybe you can ask, you can send in the chat. Yeah, after the review, I'm going to finish week 2 material. Then the major part of today's lecture is on the week 3. It's about physical system. So let me begin by reviewing previous material. We talk about quantum teleportation. So we're trying to establish an unknown state by sharing an entangled state between Alice and Bob. This is entangled. And there's this unknown state. I label this particle 1 and the entangled pair 2 and 3. Okay, so somehow the pen does not write out the ink. But anyway, so the way we do that is that we allow them to share this entangled pair in the 0, 0 and 1, 1 state. Yeah, we use laser. 0, 0 and 1, 1 state. And the mathematics goes as follows. We just decompose. There's some problem with the laser pointer. Let me see if I can change that. Yeah, looks like the PowerPoint froze. Let's see. Okay. So maybe I'll stop sharing and then maybe I will restart the PowerPoint. Somehow there's a technical problem. Okay, I stop my PowerPoint. Let me try to start this again. Okay, let me share my screen. Okay, so can you see the slide?
Yes, yes.
Okay. Let's see if it, okay, yeah, so we were here. So you want to teleport this state to B size. So 2 and 3 are particles that has this Bell pair entanglement. And we talk about this, the scheme is that you perform a measurement. Measure at 1 and 2 in the so-called Bell basis which are basically this basis states defined by the four states listed here. And because the measurement is random, you have to pass classical information about what measurement outcome you have. So the math goes as follows. You simply just write down the unknown state and the entangled state. You expand that. Because you are doing the measurement on 1 and 2, in this basis, so you like to decompose 1, 2 particle in this basis. So I just put 0, 0 into the superposition of phi plus and phi minus, and for the other 4 state as well. Then I collect so that 1 and 2 are in the 4 possibility, right? And what that means is the third particle state would be in either A0 plus B1 or the 3 other combination. So meaning that information, even though A and B are unknown, but they are preserved in the third particle. But there might be additional like phase or flip or both. You need to correct. By measuring 1 and 2, you project the third particle into the corresponding 4 possible states. By knowing which outcome, then the B side can do a corresponding recovering operation. For example, if this is the measurement outcome, you don't need to do anything on the third particle. For this case, if it's phi minus, you would need to have apply the Z operator to cancel out this to correct the phase. If it's psi plus, you need to correct the bit flip. If it's psi minus, you need to correct both, and you can use Y operation. So that's the essential ingredient of the teleportation. So any question on this topic? No? Okay, I guess it's clear, but I want to emphasize, we're using the linear superposition. We basically decompose the states, and we use the measurement hypothesis, right? So when you measure, you collect the state to any of the 4, and consequently, it also projects a third particle into the corresponding states. And then the correction is something that you can do on the B side if you have the measurement outcome. Okay. Another topic that we mentioned last time is the so-called gate teleportation. What I started with is also an unknown state in A, B superposition. And I have a plus state. Just to remind you, the plus is basically 0 plus 1 over square root 2. And I apply the control Z gate between the two. Then I measure in some arbitrary basis defined by this observable. And their eigenstates are these two. So the outcome can be the plus, which I use as equal to 0, or minus. In this case, I use 1 to denote the outcome. And we went to the mathematics. In the end, we saw that the information of A and B is teleported to the second qubit. But on top of that, there is this single qubit gate. So this is called gate teleportation. And we will discuss this in more detail in later lecture, that this setup can be used to discuss the so-called measurement-based quantum computation. Okay. For the detailed derivation, you can review the last lecture and the slides. But any conceptual question? Okay. So the next topic is entanglement swapping. This is essentially extension of teleportation, meaning that if you have two pair of entangled states, and for example, Bob has position of the two particle, he can perform the Bell measurement, and at the end, this state is teleported to Charlie. The upshot is that the entanglement between Alice and Bob is actually transferred to Alice and Charlie. So in this way, you can establish a longer entanglement. So this is used in the so-called communication protocol, or sometimes called quantum repeater, as in Dwan-looking Sirac-Zoller scheme, where you have a little segment of entangled pair. These are local, short distance entanglement. And then you can do the Bell measurement to establish a longer link of entanglement. And then you can combine them into a larger network. So in principle, this can be used to form a quantum network. So in fact, this is actually pursued in Eden Figueroa's lab. So any question on this subject? Okay. The one that we mentioned at the end of last lecture is remote state preparation. This is easy illustrated using the singular state. The singular state has an anti-symmetry. When you exchange the two particles, there's a minus sign. So you can write in useful decomposition for any single qubit state, you have a state psi and its orthogonal state denoted by psi perp. You can write these in terms of the two state, psi perp, and its exchange with a minus sign. There might be some overall phase, but the upshot of this is that if Alice performs measurement on her side, in this space is psi and psi perpendicular, she can randomly get psi. If that's the case, then Bob gets psi perp. If she gets psi perp, Bob gets psi. This means that she can prepare Bob states remotely, but it's in a random state. It could be psi or psi perp. In general, it's not possible to have Bob rotate from psi perp to psi. If you want to deterministically prepare a state, doesn't seem to be possible, except when the state is in these so-called equatorial state. Remember, these are states that if you write in terms of Bloch sphere, they lie on the equator. Okay, because the perpendicular one can be corrected by just a phase flip. So this was discussed more generally in this paper. What they discuss in this paper is the task of remotely prepare a certain state, and they want to balance the resource. For example, the classical bit communication. This is classical communication. The resource, they're quantified by the number of bits, and also the resource of entanglement quantified by the so-called E bit. Okay, but this was a research topic some time ago. So that's the review of the few topics we cover. Any question? Okay, so we're going to finish the week 2 material. Another topic that we did not discuss last time, but it's widely used in experiment and verified, is the so-called superdense coding. The purpose of this is to send classical information. But what is done is to send a quantum bit. So this is different from the teleportation where only classical information is sent. How this goes is, suppose you have any of the 4 Bell's basis state, a share between Alice and Bob, and what Alice wants to encode message, she does that by applying either identity or poly X, poly Y, or poly Z, and this in turn would actually convert to one of the 4 Bell states. And when she sends this particle physically to Bob, then Bob has both particles at his hand, so he can perform the Bell basis measurement. And then he can figure out which state he got. If he, let's say he get psi minus, that means Alice is performing identity. She did nothing, so that could be a message. That's called 0, 0, and this could be 0, 1, 1, 0, 1. So in this sense, Alice can communicate two bits of classical information by a quantum bit. Okay, so this in some sense is better than classical, because for classical information you can only send 1 bit, and that's 1 bit of information. But quantum mechanically you can send 1 quantum bit, and that would give rise to 2 classical bits of information. So the next slide shows the key property that allow you to do this. The key property is that these 4 Bell states can be interconverted to one another by local operation. So for example, if I start with, let's start with phi plus, we know that if I apply sigma z on the first qubit, the sigma z will flip psi of this particle, so it flipped to 0, 0, minus 1, 1. So this is phi minus, right? If I apply sigma x to the first particle, sigma x flip 0 to 1, 1 to 0. So this is psi plus, right? And if you flip, if you apply sigma y, which is roughly sigma x and sigma z, so you flip not only the bit, but also the phase, so that you would get zero, 1, minus 1, 0. Okay. So notice I apply on one side, on the A side, let's say A and B. But you could also apply this on the B side. It's very similar because I start with a state which is symmetric. So you can imagine you apply this on the B side, you can convert this to any of the 4 fail state. So this is why the superdense coding can be made, because I can, on one side, convert using my operation to convert this entangled state to any of the 4. Then if I have both particle at my hand, I can perform the measurement in this basis, and I know what's the state I got. That allow me to infer what Alice has performed. That is a way to encode message. Any question? Okay, this is not difficult to understand. And in fact, this also was not that difficult to implement experimentally. So what they did is you have an entangled source. This is called down conversion. So there is a UV pump. It probabilistically prepare a entangled photon. So let me just denote by this entangled photon pair. So one of the particle is sent to Bob and one to Alice. Okay, this is the other. Yeah, this one goes to Bob and this one goes to Alice. And okay, in this experiment, Bob was the person who performed the rotation that encode the message. And then he forwarded this to Alice. So Alice now has in her possession both particles. She can perform, she can perform the Bell measurement. And this is verified experimentally. But I want to point out that in the simplest setup, using linear optics, actually Bell measurement has a success rate only 50%. So meaning that you can actually extract two messages. So there's a drawback of using this this linear optics setup. But you can also use other degree of freedom. So you could use more degree of freedom. Then you can allow send more messages. So there was an experiment that my collaborator performed that they were able to actually have 3 messages in practice. So here this means using the simplest setup in practice, 2 messages. There is actually a way to make these 3 messages. Actually, here, this is 4. Yeah. But these are more detail. I don't want to discuss more. Any question? Okay, so there's a slightly advanced topic that actually is the work of my collaborator and I. But this is easy to say it, what's going on here. So remember the remote state preparation. This is in some sense similar, but this is called superdense teleportation here. You could also see the connection to the superdense coding, but so sort of in quantum sense. So suppose you want to encode message, but using phases. And here I'm using D-level system. So D-level. So I encode the message, let's say 1, the 0 state, e to the by 1, 1, etc. I'm using the phase phi to encode my message or information. And suppose Alice and Bob also have a shared entangled state, but this is in the so-called qubit. It's generalization of our 5+. What the scheme goes is as follow. So one of the person use a phase shift and apply to one of the particle, right? So you can basically shift, so the phase is imprinted to this phi particle. Okay. Then the other side, on the one side, you have to perform a measurement in this basis. It's sort of a Fourier basis. Because there's a Fourier transform. And then you compute what's obtained from the other side. So you see that if I perform and obtain this outcome, the other side, the state of the second particle is projected to this. Basically, I teleport the phase to the other side, but I created an unwanted phase. But this is possible to correct because you can use this to basically cancel the phase. Okay, and to recover the state that want to send initially. Yeah, so one of the collaborator, Bernstein, who named this superdense teleportation. Okay, but as I pointed out, this is a slightly advanced topic. If you don't understand in the first reading, it's fine. But question?
You mean Charlie? Should the Charlie be Alice?
Yeah, so Charlie, in this case, Alice, Bob, sort of Charlie, the way we introduce Charlie is because Charlie wants to encode this information and doesn't want Alice to know what the phase is encoded. So that's why I introduce Charlie. So, but you can regard this is on one side.
So Alice did nothing?
Alice does nothing. She does measurement. She does only measurement.
Oh, so in the third paragraph, there should be Alice.
Yeah, so Alice informed the outcome. So apply this, and
I mean,
this
who
should
applied the
this should be Alice.
Yeah.
Yeah, if you want to.
Who will apply the phase shift?
Charlie applied the phase shift, and then Alice performed the measurement. Yeah, if you want to have a setting
But,
of the 3 characters. Yes?
Oh, yeah.
So the thing that's unknown is because Charlie's phase is unknown.
Okay.
Okay, but if you want to treat this as a remote state preparation, then from that perspective, Alice and Charlie are the same party. Okay. So if there's no more questions, I want to enter the major topic today. So I'm going to discuss a few physical systems that are currently being used for quantum information processing. So this includes superconducting qubit, solid-state spin, photon, trap ions, topological qubits. So there are a lot of physical systems. Yeah, so I just want to give you some impression of what's being used, and there are varying degree of detail. You don't necessarily need to know all the detail, but I want to give you an overview. Okay. But there is a way to have a overall understanding is using the so-called DiVincenzo's criteria. So you use these criteria to see whether a physical system can be used for quantum computing or quantum communication. So the first criterion is you need to have a scalable system, physical system with well-characterized qubit. So our qubit will be a two-level system, for example. This will be 0, that will be 1, for example. And scalable means that you need to have many copies. You need to have many qubits, okay? Well-characterized meaning you know, for example, the energy between the two or the physical property. Okay. The second is the ability to initialize the state of qubit to some simple fiducial state such as 0, 0. But this is clear because in quantum computation, you need to start with something. That's usually the 0, 0 state. So this is state preparation. The third criterion is you need to have long decoherence time, or sometimes you can also call coherence time. So there are two different mechanisms of decoherence. One is relaxation. So relaxation means that maybe the excited states can drop and then maybe emit a photon. So this is called relaxation. And dephasing is a bit more subtle. It means the cross term, if we write in terms of density matrix, remember the density matrix rho if you write, it would be A square, A B star, A star B, and B modulo square. Coherence means that this can retain 1 or a large fraction. So if it decohere, meaning that this coefficient is less than 1. So this coefficient less than 1. So this could be it's entangled with an environment, and the entanglement increases, and therefore the coherence becomes smaller. So this is called dephasing. So the picture that's drawn here using the Bloch sphere, in this case, I think this is denoted as a ground state. So the excited states can decay. So this is energy relaxation. The time it takes to do this is called T1 time, relaxation time. T2, if you want to have a more pictorial way of understanding, is that when you flip this to an equatorial plane, it's 0 plus 1, for example, with some phase. And if you consider repeating this many times, so the decoherence dephasing happens because there's some spread of these arrows when it starts to evolve in time. This spreading gets large. Let me just say spreading. arrows. That's the dephasing. Okay. So what we want is we want these times long. Right? We don't want the qubit to decohere. We don't want it to relax. We don't want it to dephase. The fourth criterion is that we need to be able to act on these qubits with a set of universal gates. So for example, the Hadamard gate, T gate, and control NOT gate, these are universal set of gates. And we'll talk about the gate more later in the next week's topic. Of course, at the end of quantum computation, you need to perform measurement. So measurement, this is the fifth criteria, this is the second criteria. So you need to perform measurement. So the qubit specific measurement capability need to be there. Otherwise, we cannot read out the outcome. So when you see a physical system, you should ask yourself whether it satisfies all these criteria. If it does, then it can be a very useful physical system for quantum information processing. Okay. So now let me talk about various qubits. I may not be able to go through all these, examine all these 5 criteria, but let me talk about the physical system. The most natural is to use photons or light in general. The advantage is that photons are clean, the decoherence time is long. Disadvantage is very difficult to interact because if you have 2 photons, they simply pass through each other without any interaction. And also photons are easy to lose, and that could be an issue. But what's used as a qubit? For example, you could use the so-called polarization. The polarization basically is the oscillation direction of electric field. So what's shown here is the polarization. It could be up and down. So for example, this indicate up and down oscillation. This is vertical, this is horizontal. And there's something called polarizer, which can filter out certain direction of polarization. For example, in this case, the polarizer filter out the vertical polarization. So this can be used as a way of measurement. I talk about the horizontal and vertically polarized. In our block sphere, this is the Z basis. So I can say this is like that. But there's also other directional polarization. The simplest one next to the horizontal or vertical is sort of 45-degree. So if this is HV, you would have 45-degree D and the anti-diagonal. Okay. So in terms of block sphere, this would be like D and V, sorry, D and A. But there are also circular polarization. These are interesting directional polarization because the electric field, when the light is propagating, the electric field actually rotate, the direction is rotate. And this rotation can be induced by using something called quarter wave plate. You can use here quarter wave plate to rotate. So you want the left, right is in this direction. This is the block sphere picture, but actually they have, in optics, they have their own sphere called Poincare sphere, but it's a bit rotated. So with R at the North Pole and L at South Pole, D in the x-axis, A in the negative x, and then, sorry, D is in the y, and H is in the x direction, V in the minus x direction. It's just a name, but it and the sphere are similar just by rotation. So this is often used. This is used in the so-called down conversion that I mentioned. Right, so down conversion photon, it could be, this is HV or VH. You could create an entangled pair in this form. Another popular way of encoding qubit is using the time beam. It's basically just a time sequence. If you have a way, for example, if sending this, remember our Mach-Zehnder interferometer, this goes through a longer path, so it comes later, and this goes through a shorter path and comes earlier. And I could use this to encode 0, I could use that to encode 1. So timing is important in this implementation of qubit. Okay, and there you could also combine, for example, you might combine the, let me see if I could make it larger. You might combine the polarization. So this pulse, not just a pulse of photon, but also has a polarization degree of freedom. You could also flip that and rotate that as well. Okay, so that's a second way of using photons. So when I say photon, it's, imagine that this use, for example, really weak laser pulse. So on average, there's a 1 photon. So another way of encoding quantum information is really using a simple way that's called dual rail, meaning that you take either 2 poles or 2 modes. You like to call, people in optics like to call these modes. So there are 2 modes, and use the presence in one mode as a logical 0, presence of the other as a logical 1. And this was proposed, this was exploited in a scheme called KLM, Near-Laflamme-Milburn scheme of linear quantum optics. And what I've shown here is a way to implement a control ZK. As I mentioned, photons, they don't interact. So usually don't interact. So what is used here is you need to have some kind of nonlinear phase shift, and then you use a measurement to induce interaction. But this is a research topic, so as long as you know what's used in encoding, I think that's already good enough. So far I talked about photons, but you could also use the so-called laser light. It's in the so-called coherent state. Coherent states are a state of light that looks almost classical and described by these equation. So A, if you have learned quantum mechanics, you will recognize these A can be written in the position operator and momentum operator in this combination. And this is called lowering operator. And its conjugate is called raising operator. They just differ by a minus sign here. What you can imagine is there's a ladder, and n representing the number of photon states. So this is a 0 photon. And if you use the raising operator, you will raise to be a 1 photon state, and then raise again 2 photon state, etc. And lowering operator does the reverse. A coherent state alpha is a state in this position and momentum plane looks very Gaussian. So here I plot the alpha, and there's also the minus alpha. It's in the opposite location. So you could use this as a basis for qubit. So what people usually use, there are many ways, but this is one of the preferred ways, is using these superposition of alpha and minus alpha. What I plot here is not a superposition. I just plot the two curve and superpose, add them. But if you want to superpose in a quantum mechanical way, you should write this and then plot the so-called distribution on the x and p plane. It looks like this. Let me try to enlarge this. Yeah, you could also enlarge your screen on your end using the zoom options. So you see that if you use the plus side as some interference pattern, use the minus side as a different pattern. So people use these as a way to denote the logical 0 and logical 1. Okay. Yeah, so let me talk a little bit about these creation annihilation operator. If you have taken quantum physics, you probably know this, but let me just to refresh you. So if you start with the vacuum and you apply these raising operator, you get 1 photon. If you do it again, you get 2 photons, but the coefficient is square root of 2. If you do it n photon, you multiply all these square root of 2 up to n, so it's n factorial. In fact, this is probably the formula that you need to remember. So a raising operator acting on n photon states will become n plus 1 photon, but the coefficient is square root of n plus 1. If you want to represent this in terms of matrix, this would be an off-diagonal matrix. Use just one off-diagonal has these 1 square root 2, etc. coefficient. And the lowering operator basically is it's Hermitian conjugate. So it's basically Hermitian conjugate. So what you need to remember is that if you lowering the n photon state, it become n minus 1, but the coefficient is square root of n. So basically that's this. Okay. And the coherent state that I defined earlier can be written in the photon number state. These are photon number from, could be 0 photon up to infinite number of photons. So it's in a superposition, but in this particular state, particular form. Okay. So I would have an exercise that you can go through to help yourself familiarize with the coherent state and the bosonic operator. Okay, but important things, why do we use 0 and 1 state? Because you will show that 0 state only contain even number of photons, and R state so 1 state has an odd number of photons. So it could be useful in terms of error correction, because if you know there are even number of photons, it's easy to recover, etc. But I was going to give you a homework exercise on this. Okay, any question on the photonic and light-based implementation? Okay, they're really easy to understand. Maybe you just need to pay attention on the math. The next topic are spins. So the spin For example, electron has spin up and down. You could also have the so-called nitrogen vacancy center diamond. You could also have artificial atom called quantum dot, etc. So let me go through some of these. So, but I want to give you the math that we already introduced earlier. So you remember polymatrices, right? So polymatrices. They are a special case of the spin angular momentum operator. And they are defined mathematically as a generator of rotation. And they have these commutation relation. So remember, we have poly for spin. This is called spin 1/2. Sx is poly sigma x over 2, Sy is sigma y over 2, Sz is sigma z over 2, etc. Okay. This is a special case, but in general, you will use the S to denote the angular momentum. Okay, and they have these commutation relation. And in terms of qubit, then you can easily represent by the Bloch sphere. Okay. The advantage of using spin is spin ahead particle is really precise two-level system. If you use sort of photon, you could have 0 photon, 1 photon, 2 photon, 3 photon. So that's why in the coherent state, you use even photon and R number of photons. But spin 1/2 is precise two-level and can be controlled by magnetic field. The disadvantage is that in most of these, they are in the solid state environment. It's very noisy, has impurity and homogeneity. The coherence time is usually very short. Okay, so the specific implementations include, for example, quantum dot. These are semiconductor material, and they use the electrode or gate. For example, if they put a really negative voltage, and the electron would be squeezed into a dot shape, right? And they're using the extra electron at each dot. So there's some equilibrium electron, and you have one extra one that carry a spin, and the two dots will interact usually via the so-called Heisenberg coupling. It's like this form. This is, if you want, this is in the vector notation, but this is really the S, the left X component times the right X component, and also the Y component and Z component. This is called Heisenberg interaction. Okay. Another favorite one, in fact, this is a scheme that actually adopted by Australia, and there's a national effort on this implementation of qubit, is to use phosphorus doped into silicon. So they're actually using nuclear spin. So the advantage is that for this particular phosphorus is that long coherence time, because they're using nuclear spin. Okay, but I would say the advantage of using quantum dots or donors on silicon is that they can integrate very well with current silicon technology. So once we can prepare good quality of quantum dot spins, then we can integrate with technology and we can produce large scale processes maybe. But at this point, it's not yet there. Another candidate that are very popular these days is the nitrogen vacancy center in diamond. What this is that in diamond, it's these, each carbon has 4 neighbors, but at some point you will miss one carbon atom. And the nearby one, you would have a nitrogen atom to replace carbon. And you know, on this structure, nitrogen would have 2 unpaired electrons. And this vacancy, there are actually 3 electrons, but 2 of them will actually form bonding, and there will be 1 unpaired electron here. So, and in some way, this vacancy can actually attract 1 additional electron. So therefore, there will be 2 electrons. So 2 electrons that can be active. And it was shown that, and verified experimentally, the ground state, the most stable state of this is a spin 1 state. So 2 electrons would have 1 spin up and down, 1 spin up and down. If you are familiar with the angular momentum, you would add these angular momentum into the singlet subspace and so-called triplet subspace, where you have the total angular momentum being spin angular momentum being 1. Okay. Here is the level diagram. Basically, the spin s equal to 1 have 3 states, 3 sub-levels. And sometimes we use ms to denote 0 and plus minus 1. I'm sure you have learned it in modern physics or in chemistry. This is the lower 3 levels shown here. And somehow it was split. These 2 plus minus 1 is split relative to the 0 state. So this is due to the environment and nearby nucleus. The advantage of this is the coherence time can be enhanced. It's usually from micro to millisecond, but it can be enhanced to really long coherence time. And yeah, I show here you could also use sometimes you would have a nearby carbon being an isotope, carbon-13, and that has a nuclear spin that you can use for quantum operation. And the combined energy levels is here, but I don't want to go to the detail. In a sense, if you have a carbon-13 has a nuclear spin, it would create further splitting, and that allow you to use the extra level to perform information processing. And this is an active research area. So any question about the spin qubits? Okay, so you guys are quiet today. So the next one is also a very popular one, is using trap ions. So as you can see, there are some particle trap here. They are in fact ions that trap using electric field to confine these ions, because the ion have repulsion. So this form a chain here. You could also use a chip. This is designed from the Sandia National Lab. The way it goes is in principle, you can use the so-called hole trap. You use 4 rods, and for example, the light green are actually used in the oscillating field, and the darker green has an interesting design. There is a center rod and there's a gap, and there are 2 tiny ones. The center one is in some fixed DC voltage, but the outer one are grounded. And this is the potential you would get, but it's the details doesn't matter. The upshot is that it creates a quadruple or some kind of saddle shape potential. It's like a saddle on the horse, but because the AC field, you could actually creating a potential which is stable. So on average, you have a potential which is very stable. So they can trap very narrowly in this direction, and because these are ion, they repel each other, so they spread out a little bit more like this. And you can see the spacing. You have larger spacing because there are fewer charges along the edge. So the way they encode qubit is you use some level called hyperfine levels as qubit state. How many of you have heard hyperfine levels? Maybe you can use raise hand. So a few of you. Okay. Yeah. So I'm showing you some of the levels here, but next page I'm going to explain what hyperfine is. So these are the levels, for example, but I'm showing you according to which group they use. For example, a company called IonQ. It's actually led by a prominent physicist called Chris Monroe. They use ytterbium, and these are the so-called hyperfine levels, and they use 2 of them as the qubit levels, 0, 1 here. And for example, there's also calcium that's been used, barium, and also other ions. So these are the levels. So the detail is not important. Even I don't remember all these levels. So you just have to look up. Unless you are working on particular atoms or ions, then you know the level very well. But the simplest atoms that you have is electrons with protons that forms hydrogen, right? So I'm going to explain to you what hyperfine structure is. If you have not heard it before, this is where you're going to hear it. But you probably, if you have taken modern physics, quantum physics, you probably already know this. But let me just make sure that we on the same page. So you all know hydrogen, proton, and electron. This is the simplest Bohr model. Electron orbiting and has energy level like this, right? Minus 13.6 eV over n squared. So n is sort of levels here. N, so n equal to 1, equal to 2, etc. So I'm showing here vertically, this is minus 13.6 eV. This is minus 13.6 eV over 4, okay? So n equal to 1, and you know from chemistry, there's an orbital 1s, n equal to 2, you have 2s and 2p, right? And in these simple Bohr model, these two levels are sitting at the same number, so they're called degenerate. Okay. Do you have more levels? You could also have 3s, 3p, 3d, etc. N is called the principal quantum number. But in fact, if you consider relativistic effect, because in the case the kinetic energy is not mv squared, it's not p squared over 2m. Relativistically, it's not. So you need to take that into account. And then if you have electron spinning, so electron orbiting, you can imagine that it looks like from the electron viewpoint, proton is spinning. So proton will create some orbital spin moment that would interact with the electron spin. So this is called spin-orbit interaction. So we usually use the L to represent the orbital. And I already introduced this as the spin. And now you have two objects that are of the property of angular momentum. So we call this J is sum of the two. This is total angular momentum. And in fact, the phi structure, it turns out if you include these effects, these two orbitals, in fact, there are three orbitals for P, they would split. So they would split in a way, let me erase this, in a way that determine on the total angular momentum. So if you haven't seen this before, there's a notation that's been used. L is the orbital angular momentum. So like using S is actually L equal to 0. P is L equal to 1. D is L equal to 2, etc. So here I'm basically saying that L equal to 0. And J here is the total angular momentum. So J, where I use lower j, is L plus S. So because my spin is 1/2, the electron has spin 1/2, and orbital is 0, so you can have 1/2. 2 is the principal quantum number. And the p orbital actually split into 2. One is labeled by 2p 3/2, 2p 1/2, the other one. So they get split. And the split depends on the j. So the j depends on this number on the right bottom corner. So the larger j is, the higher the energy. Okay. So this is the so-called phi structure. And this is the correction. You see the expression. The details is really not important, just to know that the levels, initially they are degenerate, are further split into some structure. This is called phi structure. And I guess people later find there are more structure, so they call them hyperfine structure. The hyperfine structure is due to the interaction of electrons, spins, and nuclear spin. So this is the electrons' total angular momentum. This is nuclear spin. Yeah, so we have more and more symbols. And if we take the entire system, including nuclear spin, we would have angular momentum called F. The effect is that because nuclear spin interact with electron spin, the level can be further split. So for example, I just show that the S 1/2 level is further split into 2 subsets. And the lower one is called singlet, the upper one is called triplet. And for example, for hydrogen, this is the famous 21 centimeter. You will see the signals from the universe that has these, if you look at some clouds of hydrogen that are in the universe, that you can see that they have some light that emit, and it's shown to be 21 centimeter. So, well, actually by measuring the wavelength, you know that these must come from hydrogen. So this would be something that's quite useful already. So I know this is probably a advanced topic if you have not heard it before, but this is how the hyperfine structure came about. So if we go back, right? So remember, there's S, there's also P. If you go back, you see the symbols. So there is the S, and there's also F, right? So this represents the phi structure. When you see F, I guess maybe they want to call this hyperphi structure, F. And you see that there are sublevels. They show this slightly differ because they could be further split, can be further split by a magnetic field because these are spin states. Okay. And so if you can control the transition between any of the two, you can use a pair as a qubit. But as I said, these are not the natural because you have so many levels. They may come into play, affect your fidelity, cause decoherence, etc. But additional level offer you additional control. Okay, so that's hyperfine structure and the ions. Okay, any question on the phi structure? No. Okay, so another set of qubit used are in a neutral atom. The reason we want to use neutral atom or natural object is because their property are well characterized. All the atoms are the same atom, same number. They should have same property. So you don't need to characterize, like if you use artificial atom, for each atom you need to know its property. You need to perform some calibration, but if you use something that already made natural, then you know all the property. So here I'm showing you the phi structure of rubidium. So remember, we have these S and P. This is exactly what you already see. And here, the phi structure, okay, the phi structure of hydrogen and the rubidium is similar. And it has further splitting due to interaction with nuclear spin. This is the hyperfine structure. So in Professor Schnabel's lab, they use rubidium. So I guess group members from his lab would know this very well. So this is like a famous splitting. In terms of frequency is 6.8 gigahertz. And they can use some of the sublevels. Let me see. Yeah, you can use some of the sublevels as 0 and 1. And shown here is the further splitting by magnetic field. Okay. So they can trap these in the so-called optical lattice, either 2-dimension, 3-dimension, or even 1-dimension. So what I show here is a review article in Physics Today by Weiss and Sapman. They talk about how to control, address particle, apply gates. So in fact, The next slide I will show setup using what Sapman's lab in Wisconsin is doing is using the so-called Rydberg atom. So what Rydberg atom is that it has really high n number. Remember, n is this number, principal quantum number. If n is large, meaning that electron in a hydrogen-like atom, they are very far away. So if you have two such Rydberg atom, they may overlap, right? So in fact, they were able to take this property to design an entangled gate. So basically what it has here is they use two hyperfine level to define their qubit, but they take advantage of the Rydberg atom being really large radius of orbital, and they overlap. So if they overlap, if you try to bring, for example, the one into these hyperfine state, if you have two such atoms trying to cycle to these high orbital state, they will interact, and that interaction will give rise to some phase. And this is usually called a Rydberg blockade, and they can use this to get a control Z gate. Okay. Any question on the atoms, neutral, ions? So I don't think I will not be able to cover everything today. So let me see if you have questions. We're approaching the 4 p.m. So what I'm going to do next would talk about superconducting qubits, and then let's see, and maybe topological ones as well. So maybe let me pause here to see any question. So there is not much mathematics, but there are some detail of the structures of the way each system used as qubits. So you only need to have an overview of what is used. You don't need to really know the detail operation. When we need it, we would specify the detail. But one of the things that I like to emphasize is the superconducting qubit, because this is the one that we'll be using. For example, the IBM will use the transmon to perform some computation. Okay, any question? Okay, if not, we'll end today's lecture here and I will start recording.